Okay, so we are going to design the sensor board today. So I have a picture of how it looks like here from what I have designed or come up with. So the sensor board is going to have GPS, accelerometer, gyroscope, a magnetometer here, sun UV sensor, temperature sensor, and then I've listed the communication protocols that will be used for the different subsystems or different sensors, and they'll be connected to, or rather through a PC104 bus, which is a common standard for CubeSat, and then that will be routed to the motherboard for processing and data collection. So let's design this, let's translate this into a schematic. So I have open EZDA, and I've created a project called it sensor board. So I'll open the schematic here. Schematic, expand this a little bit. And let's start with, let's see what we start with. Let's start with the accelerometer first. So the accelerometer I'm going to be using is the ADXL 345. ADXL 345. So let me open Google just next this guy. So I'll open Chrome. Okay, so here I can search for ADXL 345. So this is the chip I'm talking about. So I'll copy this number here and paste into ZDA. Oh, okay. Paste this, copy, then paste, enter. This is the part. So it's not in stock. Okay. It's not in stock. Let's look for another one. Let me expand this guy. Copy that. Paste, enter. Okay. So this is ADXL 345B whatever is the same. So there's a slight difference, but it's the same. So let's design the schematic around this part. The first thing we see is that it is using, you can actually use SPI or I2C, but I'm going to use I2C for communication. It has the SDA pin and the SEL pin. The first thing we do, we are going to supply it with 3v3. So the first thing we do is add a VCC here. This VCC is going to be, okay, I can use a connector for that because it will be coming out, it will be coming from a different board. So let me use this as a VCC somewhere here. Route that. I'll call this 3v3, 3v capital V. Okay. Then next thing, ground it. So ground that, ground, and ground. Okay. So the next thing is interrupt pins. I'll break these out. So I'll break these two interrupt pins just somewhere there, the other one there. Then label them. This is int 2. This is int 1. Okay, not connected is not connected, so I just put a not connect label there. Reserved is for internal use. I'll leave it there. I'll leave the address for now. We'll look at the datasheet for that. SCL and SDA. So this is I2C. So for that, I2C requires pull-up resistors. So I'll look for pull-up resistors. You can use somewhere between 4.7K and 10K. So I'll use 10K. C05 10K resistors. Okay, so copy that, copy, paste, and it's right here, so you can place that 10K. So I'll place one there, another one here. Then these two are pulled high, so I'll pull them high to 3v3, 3v3, and then one of them is connected to SDA, another one to SCL. And then what I do next is obviously label these nets to be able to break them out later through our bus. So this is okay, this is not supposed to be, this is supposed to be here. Okay, so this is SDA. So I call these AD SDA, just to stand for ADXL SDA. Then I'll call these AD SCL. Okay, next reserved, I put a not connect flag. VS is supposed to be connected to 3v3. So I'll just put this a little bit, connect a 3v3 to VS over there. Chip select, it's, you can see that it has a hash here. So what this hash means is it's active low. So to be able to select this chip, because I2C uses a master slave configuration. So to be able to select this chip, we need to connect it to, from their datasheet, they are saying you need to connect it to 3v3 for some reason. They are pulling it high. But for my case, I'll pull it low because it's active low for now. So we'll confirm that later, but for my reasoning, it's supposed to be low to be able to select that chip. Now let's open the datasheet for this person and see the address part. I just want to explain something on the addressing, especially for I2C devices. So to easily open the datasheet, you can paste the part number here, then click on the datasheet. Then you open this. I want the bookmarks. I don't think they don't have things in Chinese. What? Okay. So let me look for ADXL. ADXL 345 datasheet. Datasheet. Let me open this one from SparkFun. Okay, it's taking some time to load, but let me look. I want the addressing. This is a breakout board, so they are just explaining how it works. Okay, let me see for this other one. Okay, this is the one I'm looking for. So I want to look at addressing serial communication. I square C, page 10. Okay, so you can see with the SDO address pin high, the 7-bit I2C address for the device is this, followed by the read write bit. Okay, this translates to that for write and this for read. So what we want to do is have a 7-bit address here, which means that we have to pull SDO address pin high. We have to pull it high. And then they are saying it translates to that. And then alternate address is this one, can be chosen by grounding the SDO alt pin address. This translates to this command for write and A7 for read. So what I'm going to do, I'll choose this second one here. Is right here. Yeah, I'll ground SDO address pin. You can choose whichever you want, but I'll choose this address for now. So that means I have to ground it. Let me put it here. So what I'll do, I won't just ground it. Let's see. Address is grounded directly. You can use a pull down resistor if you want, but to be on the safe side, let's use a pull down resistor here. So yeah, I'll use 10K. Place it right there. Okay, so the next thing we need to do, sometimes you need to put a little note on your schematic to be able to remember. So when we ground, the address will be 0x53 in hex. So I can like put a little note here and say address is 0x53, address 0x53, place, and then you're told 0x-A6 for write and A7 for read. So this will help a lot in when you're writing the firmware. So read is 0x-A6, A6, yeah, write for write, sorry, is for write, and read is 0x-A7. Okay, save that. All right. So I think we have everything we need at the moment. So if we did not have a 3v3 power supply, if you are giving it 5 volts, we would need a 3v3 regulator here, but we are good for now. Okay. So the next thing we design is, let's see. Let's look at temperature sensor. Temperature sensor is supposed to be easy because I will be using the LM35 temperature sensor. So I had options. You can use a thermistor, you can use LM35, but a thermistor requires calibration. So I don't want to do the calibration because you might get it wrong, or I mean, you might not get it wrong a lot, because the problem is you'll be calibrating it on Earth. I think what I'm thinking is that unless you have very good testing conditions, use something that does not require calibration. So I'll use the LM35. So let's see whether it's available on LSC. LM35 search. Sometimes this site hangs for a reason, I don't know why. LM35. Yeah. This is LM35. It's not that one. So LM35, let's say temperature. These are very different things. These are power converters. You can look, you can, if it's not available, you can use another one. You can use DSB 1820, I think. Oops, it's not that one. It's DS 18P20. Yeah, this is a programmable one-wire digital thermometer. Let's look for that. DS18B20. Yeah, you can use this one. Is it in stock? Yeah. TO92 package. Let's look for SMD package. Okay, seems like what they have is TO92, so we'll use just that. The one that is in stock is this one, so copy that number, bring it to EZDA, Shift F, paste, and place. So you place that. Now this is using a one wire. So if you don't know what one wire is a method, is a communication protocol that can carry power and data over the same line over one wire, ideally. So you can see it has just three pins. If I open the datasheet, these things are in Chinese, man. All of them Chinese. Analog devices. Let me open this one. Okay, so 9-bit, 12-bit. It's a programmable resolution, whatever thermometer. So this one provides digital data. It's the same as LM35, but LM35 will give you analog data. Okay, so I wanted to look at if there's any other schematic. This is e.t.c, so let me just remain with TO92. There's no problem. Okay, supply voltage 3 to 5, so I can use 3.3, which is okay. Let's look at these are things we can look at them when you'll be doing the driver, we'll be writing the driver and the circuitry. Okay, so you can see on the one wire bus, it's if we need to power it with an external supply, we can use VDD on the external supply ground. Then on the one wire bus, we pull up using a 4.7K. If we need to use the parasite power, we need a MOSFET here, pull up. So this I don't want to use this first of all because it adds additional components. So I can use this with an external supply. So what we need additionally is this 4.7k kilo ohm resistor here. All right. So let me use this. Okay, so I'll look for 4.7. 4.7k is 0.05. 4.7k resistor. Copy that. This one is not in stock. This one is the one that has the most. Okay, by the time I produce these boards, I hope most of these things will be in stock. So I'll copy that, bring it here, Shift F, paste, enter, place that. So I can place it, okay, that way. And then round it. Okay, so pull up through the one wire bus. So I'll pull this up. Let me arrange it a little bit. So add a wire here, and then our power is 3v3. So put that there. All right. VDD is 3v3. So yeah, I think we're good. Okay, that is in order. So the rest of the information, memory, whatnot, we'll look at it later. Okay, so what's next? Temperature is check. GPS. Let's look at the GPS. Let's look at the GPS. So there are two options when you're using the GPS. You can use. I want to use a uBlocks Neo modules. So there's Neo 6M and Neo 8M. So Neo 6M is good, but it consumes a lot of power. So from my previous usages, it consumed around 37 milliamps approximately. And Neo 8M consumes less than that by around 10 milliamps. So it's around 27 or so milliamps. Number two, Neo 8M has higher accuracy than of around 1.5 meters than the Neo 6M module. Now, for low power applications like CubeSats and drones and stuff, you need a device that will use the minimum battery as possible. So let me go with Neo 8M module. Now I'll search for it here on let's see, obviously as we've been doing. So let's look for Neo 8M, Neo 8M, Neo 8M. I don't know whether it's available actually. It's available for pre-order. There's 7M to all of these things are not in stock. Which one is this? It's not even GPS. Okay, seems like it's not available. So you want to use it, but it's not there. Look for Neo 6M. 41 parts. It's not available too. Okay. Next, look for GPS. Let's add a keyword here and use GPS. Neo 6M GPS. GNSS modules. What's this? Nope, not that one. All these ones are for pre-order, meaning they are not currently in stock. Okay, so we pause that for the moment, and let's look at the sun sensor. Sun sensor. Sun sensor I want to use is it's called TEM T6000. This one right here. Now, this device can only sense the sun when it's outside the CubeSat. So it means that it has to be on the body panels. Yeah, it has to be on the body panels. So what happens is, let's open the image here. What happens is that it has to be placed on, so because a CubeSat is like 6 sides, it has to be placed on all the sides. First of all, for redundancy. Second of all is to have like marks to be sure of where the sun is for orientation. So if this is a CubeSat, where is the image? If this is a CubeSat here, it means it needs to be placed on all these. So I want to place mine on all these surfaces. So I'll need 6 of them. Which means I need like to connect them with a wire to the sensor board. So I won't place this guy here. I'll place the connector. So if I look at the footprint, you can see that it's assumed that it will be placed directly on the board, but I don't want this. So I want three connectors for that. So I can use header pins and solder them, and that is exactly what I'll do. I'll look for HDR 2.54 and 1 times 3. Okay, 1 times 3. So I'll place 6, 1, 2, 3, and then I can copy them. 6. All right. So oops. Open the datasheet. Let's see what it requires for connection. I hope it's not in Chinese too. Okay, good. Yeah, anyway. Here's the power supply. Electrical characteristics. This is a open collector emitter. It's not written. I can't see it. I'll assume. Okay, we are using 3v3 here. These are test conditions. We are using 3v3. So which means this thing is because it's, I assume it's using a voltage divider mechanism. Let's confirm that. Mechanism. Which means that its data is in analog form. Oops. What's that? Okay. These are mechanical dimensions. Okay. So go to images. Good. This is what I'm looking for. So you can see it is using a voltage divider thing, kind of thing. So this is the signal is an e.t.c. Okay. So I'll have a signal here. Then I'll have 3v3, and then I'll have ground at this point. Ground. So you put this here, and then label it as, let's call it sun sensor sun. Let's call it sun 1. Sun sensor 1. Actually, all of this was useless. Let me delete that and copy paste this right there. Yeah, copy this again and paste it here. Okay. This is sun 1, this is sun 2, this is sun 3, sun 4, sun 5, and 6. Okay. So I think this is in order. So I'll just group these things in, just to have some order. I'll put that there and have text, sun sensors, sun sensor. Make it bigger a little bit. I just need this name here, just to label which sensor it is. Okay. Next, arrange it a little bit. So I'll put that one right there. So this is the, oops. I'll put that on right there and copy this temperature sensor. I can put this one there. Okay. So this guy can be right there. Okay, paste. I'll call that ADXL 3345 accelerometer. Okay. So move this a little bit. Copy, paste. I'll call this sensor board. Sensor board. make it bold and then make it 8 10. Okay, so next thing we need to design is the gyroscope, but I think, where is it? Yeah. Let's look at this guy first of all. That's right here. So a DXL for 345 is an accelerometer only. It's an accelerometer only. It does not have a gyroscope. I hope I'm right. Am I right? Yeah, it's an accelerometer only. There's no gyroscope. So what I'm thinking, you can do like sensor fusion. You can have two. First of all, I chose a DXL because it's highly sensitive and it has a larger bit range than the MPU 6050. So MPU 6050 combines both the gyroscope and the accelerometer in one. So we can use the 6050 for gyroscope and also for acceleration, and then combine all of those readings, get the offsets, and I'm sure we'll have better measurements. I think we'll have better measurements. Someone would have used just an MPU 6050 for that, which is okay because it combines both the gyroscope and the accelerometer. Okay. All right. So that means we need to look for the MPU 60. So our primary accelerometer will be the ADXL, but this guy will be secondary. I mean, it doesn't hurt though to have both. Control V, place. So you can place this right there. The first thing is to ground it. That is the ground. It is right here. Then a number pad. You can ground it, but I won't ground it for now. Next thing is not connect, so I just put that there and in right there. VDD 3v3, so I can copy paste VDD. Okay. Next thing is STA and SCL, so I just pull them up. I can pull them up to 3v3. So connect this one there and SCL, and yeah, just connections 3v3. That's okay. And then we label the pin. This is SDA, SCL. Now we label this AD. So you can label this MP SDA and MP SCL. Okay. Reserved. So for the reserved pins, we put not connected. We break these out. Can break these out. Auxiliary and auxiliary. Good. Okay, so let's open the datasheet for this guy and see what they recommend us to use. All right. Gyroscope, accelerometer, e.t.c interface. These are clock timing diagrams. Timing diagrams. Let's look at the accelerometer specifications. Is a configuration data. Recommended power and procedure. I think that is in programming. They have a temperature sensor, serial interface. Let's see. Okay, let's start here. Okay, so this is what I'm looking for. So typical operating circuit. I'm using a PU6050. So you can see that they need us to use 2.2 nanofarads, 10 nanofarad to the ground. 80 is broken out, 100 nanofarads to ground. So you have a bunch of capacitors to ground. All right, so I'll add these 100 nanofarad capacitors. Just close this one. This will be C005 and grid F. Copy that part number, paste, place. So we have that one. Let me just open it just right here. Okay. We have 100 F to pin 10, which is the ground. I'm pin 10 to ground, so pin 10 is right out. So copy that, paste. .2 nanofarad on pin 20. Pin 20 is CP out. So 2.2 NF. 2.2 C005. 2.2 NF. Yeah, that one is okay. Looking for part number here. Yep, copy that. Shift F. Place. I didn't even look at the price, but okay. We'll deal with that later. That's arrows pin 20. Pin 20. They can share the ground here. Okay. 10 NF on pin 8. Pin 8 is logic pin, so 10 NF. This is 10. farads. Just to be sure, it's 10 nanofarads. So I'll copy this number, Shift F, enter, place it right here, and ground. Okay, so I'll just label these pins. So aux DA, so this is MPU aux DA. Just make them longer a little bit to be able to just look neat. Then I'll delete this and I'll copy paste right there. And this is aux CL. Okay, this is e.t.c, this is MP what? e.t.c, is it used even? Pin 9. Yeah, e.t.c. MP e.t.c. This is interrupt is pin 12. It's an output pin. Basically, it's used to, anytime you have a data, it can interrupt the procedure of the processing of the program and send data to the processor. You can set it to operate in that mode too, but anyway, we'll look at that later. So I'm setting MP int clock S pin 1, so clock in, that is clock in. Okay, pad is basically a thermal pad that is connected on the lower side of the PCB. So you can ground it if you want, but for high reliability, I'll ground it. I think everything is okay. Pin 19 is not used, so I'll add a not connect tag there. Right, so we said we are going to use this as the secondary accelerometer and the primary gyroscope, and then perform sensor fusion on the data in the attitude control algorithm, or the attitude control algorithm. So this is MPU 6050 accelerometer and gyroscope. Okay, so the next thing is GPS. We said you look at that accelerometer. We have that, we have this, we don't have a magnetometer, we have these two, so we remain with the magnetometer. So let's look for a magnetometer that we can use. MLX 9393. MLX 9393. Just looking for parts here, parts that we can use. Is in stock. Okay, magnetic sensors. Okay, so we'll be using magnetometers to measure the magnetic field of the CubeSat, and then use that to control the magnetokers for detumbling and orientation for carrying out a mission. For example, you need to point downwards at a given specific coordinates. So magnetokers are good because first of all they are not mechanical mechanisms, so the chances of wear and tear is little, and they consume less power obviously, and they're cheap, so we can use them. So that's why we need a magnetometer to measure the magnetic field and then interpret that into useful data or useful information. So I'll place this guy into EZDA. Okay, the next thing obviously we do datasheet. So for some reason it has opened on a different window, but I'll just open the datasheet here. We look at it. Triaxis whole technology 2.236, which is okay. So this is a magnetic field sensor, can be reprogrammed. Okay. So communication e.t.c, which is good. Okay, block diagram. Okay, application examples. I think I've looked at that. So I need the connection diagram. This is a timing diagram. For now, I just need the circuit. Okay. So here it is. So they have given us the addresses based on these two pins, A0 and A1. SDA, they are pulling it high, R1 and R2, 10K, as you can see. C1, C2 is 100 nanofarads, C1, C2 is right here. So VDD is pulled, this is filtered to ground, VSS. It's just a typical connection, normal connection. So I'm gonna use this. So what I'm gonna do, open it on the right. Shit, okay. Okay. So I'm not using SPI, so that's that. So I'm gonna use this diagram here. So what do I need? I need a 10K, which I have, 100 nanofarads I have. That's all. And then I can choose the first address. This 001. Let me see whether this conflicts with. Remember, we have another address here. So let me see whether that conflicts so that I know what to choose. Calculator. I'm just going to open a converter here for that purpose and paste this number. This is 1100. Okay, 1100. No, this is 001. It's good. So it's not conflicting. This is C. It's not conflicting. We are good. So you can use the first one, which means we set A1 to VSS and A0 to ground. So let's start by doing that. So A1 to ground is A1 to ground. A0 to ground to both of them to ground, like that. So this is 0 0 to 0B 1 2 3 1 1 0 0. Read, write. This is very useful for the driver part. So what is this? This is the address. Okay. All right. The next thing is you pull these things up, copy those two resistors. Where's SDI and SCL? They are right here. So pull that up to 3v3, copy paste. The next thing, obviously, we label, net labels. So place a net there, place a net there. This is MLX. So I can call it magnet SDA and mag SCL, like that. Okay, so we have handled this part right here. Next thing we do is we supply it with power here and filter it with a 100 nanofarad capacitor, which is right here. Copy that, paste to ground. So I'll add ground here. Okay. The next thing is obviously the SS. Where's the SS? It's right here. So I can just connect this to ground like that. Not connect to that. And this other one. Okay. So I'll just move this a little bit. Just like that. Pin 1. The interrupt or trigger. I'll break it out. Let's move this a little bit. So this is the interrupt mag int. Okay. Miso, I'm not using Miso is not using that. That's for SPI. Not using those ones. Pin 2 is SNP CS chip select. Chip select is pulled high. So that is pulled high. So I can, so it's not pulled high, it's connected directly to 3v3. I can do that, but that will look ugly. So what I'll do, I'll move these ones right over there and then connect from this point to that point. And I can put these ones right there, like that. Okay. Interrupt P7, break it out to so Alt N, put that. This is mag int. Okay. And C is not connected, so put that there, that one there. Okay. An Apple pad, I can pull it to ground. All right. What is remaining? Int, interrupt trigger. I think everything is handled. There are two int pins here. This is int, that is int. So I can rename this to int TLG. Nope, I think that is in order. Let me put this one there. Okay. So VDD C1, where's VDD? VDIO is right here. And then there's VDD. VDD is right here. So VDD is connected to 3V3. Wait a minute. This is VDD 3.3 volts. So this one should be connected right here and filtered with a capacitor to C1 100 nanofarad to ground. So I'll put this one down here and do that and copy that to ground. So they're saying the IO should be 1.7 to VDD, which is okay. You can use 3V3. And that's that. I think we are done with the magnetometer part. Is there anything else I've forgotten? I don't think so. Okay. We'll review the design later, but for now, it's good. For now, it's good. So put that there. This is called, copy that number, paste, magnetometer. Okay. So this video has become too long, and I think we have everything we need except for a GPS. So in the next one, we'll design the GPS and then add this bus. We'll design the GPS and add the bus to the sensor board. And with that, I think we'll be okay. So see you next time, and have a good one.